All right. So everyone, thanks for joining. I know we've got a few people still coming on late. It's probably your lunch break, unlike Vincent, who it's his dinner time. This is just I want to try to organize these whenever possible. So I'm thankful to Vincent for volunteering. Basically, it's just a cool way to keep people engaged and get members of the Slack community together and nerd out over things that we're maybe like-minded or not about. I don't know if there's any adamant frequentists on the call, but um, I'll be recording just to share with friendly text-based people that couldn't make it, um, and I'll share it later. And I think Vincent will allow room for question and answers at the end, so you'll be able to unmute yourself if you want to ask a question, or you can type it in the chat. Either way, but a quick overview of who Vincent is. He is an algorithm designer at Go Data Driven. Are they based in Amsterdam, Vincent?
Yes.
Okay. He's co-chair of PyData Amsterdam, an RStudio training partner, and organizer of the Applied Machine Learning Meetup in Amsterdam. And he runs a really cool blog, if you haven't checked it out, at koning.io. All this info is in the email as well. And his company is hiring, so you could talk to him on Slack if you're interested at his Koning username. But go ahead. I'll stop talking now. So it's all you, Vincent.
Cool. So thanks. Just there's still a weird, annoying sort of echo, but if that persists, that's fine. I'll just remove my headphones as you guys.
Everyone's on mute. If anyone's not on mute, just kindly mute yourself. I'll go on mute now too, Vincent.
Cool. And there's still a bit of weird echo, so I'll just remove the headphones. But I guess it's fine because you guys can sort of hear me and just scream if that's not the case. But yeah, my name is Vincent. I really like this Slack channel. It's sort of weird that you meet people in the conference once and then suddenly there's more people you meet, but online. It's also kind of hard to explain to my girlfriend that I have to sort of do a conference talk to a bunch of strangers and I don't know that. But today, the goal is that I'm going to talk about some Bayesian things. It's a field of math and a field of probability theory that I think is super easy to apply and it allows you to think in different ways. The talk is split up into 4 main topics. I'll just discuss the introduction and the basic math first, and then I'll just introduce this darling example with a small riddle and make it sort of hopefully a little bit clear that there's just a bunch of these problems that they're so much easier to do if you just apply Bayes rules. After that, we'll talk a little bit about Pokemon and a use case that where Bayesian thinking shines there. And then I'll try to give a little bit of a preview of what I think the future of machine learning might look like, because this Bayesian thing is actually getting bigger. So to just get started, very basic Bayes rule. I think you've probably seen something like this before. Hopefully in some sort of probability theory class or maybe something on Khan Academy. We usually have this weird notation where we say something like, hey, the probability of A given B, well, that's the probability of A given B, A and B divided by the probability of B. And there's all sorts of maths around it, but you can also just make a very pretty picture. Here you see a nice little chart. We can pretend that I'm rolling a couple of dice, and I could be rolling 1 dice or 2 dice or 3 dice or even more. And here you see sort of a sample distribution of how many eyes in total I might be rolling. And in this example, I hope it's fairly clear that the more dice we roll, there's a bit more variance, and this is kind of like a nice little probability distribution. And the cool thing about this as an example is, if you look at it this way, I could say something like, suppose I'm rolling 4 dice, then you can see the number of eyes that you would expect. But conversely, what you can also do is you can sort of flip it on its head and you can say, suppose that I know that I saw 20 eyes, how many dice might I have rolled? And the whole point of sort of Bayesian thinking is that you stop worrying about making a prediction with a basic model, and instead you start thinking about things as if they are probability distributions. And what I'll try to do now is I'll go over the math very briefly, but I hope I will show you that modeling things in the Bayesian way give you lots of benefits. So let's do a very basic textbook example. Let's just pretend that there's this disease, and a person has a 1 in 100 probability to have this one disease. And the authorities are kind of worried, so they decide to test the population, but the test isn't exactly reliable. it gives more than 1 out of 100 people a positive test result, which basically means that you might get a positive test result even though that you don't have the disease. In fact, given that you have the disease, the probability of getting a positive test result is only 65 out of 100. With this information, you probably feel the textbook example coming up. You can ask yourself, given that you have a positive test, what is actually the probability that you have the disease? And I'll glance over some of the math here just to keep it brief, but hopefully it's somewhat clear that you can fill in a formula like this. You take the quantities that you knew, like we discussed how many, what the probabilities of the test is positive, and you fill everything in, and then knowing these 3 probabilities, you can calculate the probability of getting a disease given that the test was positive. I hope at this stage I've not lost anyone yet, because this is material I hope to glance over quickly. Later we can discuss it more in depth, of course, but we've just calculated this one quantity. What else can we calculate? Well, I can also maybe calculate the probability that you have the disease given I just did 2 tests, or maybe even 3. I can imagine that after only 1 test, there's some degree of certainty that I have a disease. And surely if 2 tests say that I'm positive for the disease, the probability here should probably increase. Well, there's all sorts of ways to calculate this, but one thing you probably want to realize is that the probability of getting a positive test result is not independent of having the disease. In fact, you can split it up. You can say, well, the probability of getting a positive test result is either I have the disease and the test result is positive, or I didn't have the disease and the test result was positive. And it's kind of nice. We can think about these sorts of things in a sort of calculus logic kind of way. And if we expand like this, we should realize that, hey, this is something we knew. This is something we knew. This is something we knew. This is something we know. And we can calculate this bit. Extra details for math. Either way, you can now also calculate the probability that your 2 tests are positive. Ask me questions about this later. This is stuff I hope to glance over. We can do the math, but hopefully you get the same numbers. And this is kind of nice, because we started with only a couple of quantities and we were able to infer more than we knew before that. Now actually, just by knowing the probability that if you do just 1 test, I can infer what it might be like if you did 2 tests, or 3. So from just a little bit of knowledge, we can infer a lot of other knowledge. And that's a powerful thing. In fact, we can look at this from a graphical kind of way. So what I can do is I can say, hey, I know that if you have the disease, what the probability is going to be for the test result. And I can expand this. And I can expand it further. And this is just a notation. All the math, we've done that before, but I hope we can start appreciating this notation. The idea here is, given the disease, the probability for the positive test results are set. And you might not realize it yet, but something very powerful has just happened. I can imagine perhaps that I might only know the first 2 test results. And even though initially I only knew about this probability, we saw before that we can apply inference. We can basically say, hey, what's the probability of the disease given only these 2 phenomenon? And we can take it a step further and say, well, because then we know the disease probability, we might be able to infer the odds of getting another positive test result. And well, okay, this is again the math, so we'll just skim over it. Long story short, this is, well, I don't feel like talking about the math too much, but we can do this as an exercise later. But the main thing that is kind of amazing, I hope, from this picture, while I'm making the prediction, I don't really consider these variables missing values. I just consider them things I have to predict. And if there's one thing that's unknown, or 2, or in fact everything is unknown, the graphical model doesn't care. So if we're able to model things this way, then suddenly we get these weird properties. We get these properties that say that I can have missing data at both prediction time as well as training time. And usually random forests and neural networks don't like this. I also end up with some sort of model allows me to completely explain how everything works. GDPR is a thing that's going to be happening soon. And with a model like this, I can very explicitly say what is causing a change where, because I've defined this myself. We have a model, if we model things this way, then we have a model that's robust against missing data at prediction time, but also at learning time. And we can explain everything perfectly. These are things we very much care for. And we can actually model a lot of things this way. Very simple thought experiment. Suppose that we have a data set with millions of patients that in total have something of 600 symptoms and 100 diseases. If we were to design a probabilistic model for it, we can probably imagine that you either have the symptom or you don't, and you either have the disease or you don't. So just like before, we might have some graphical model like this. For the disease situation with lots of diseases, we probably have a situation that looks a bit more like this. And these are somewhat older systems, but you can definitely imagine that this is maybe a symptom that belongs to these 3 diseases. And we have other symptoms, and there's a bit of overlap. But you can imagine that if you're a doctor and you have a system like this, that you can say, hey, I want to test for this symptom and that one. And you can then ask the system questions like, what's the next system I should test for to rule out this naughty disease? This way of modeling, I hope, intuitively, feels rather powerful. And it feels a little bit strange that in this day and age, instead of maybe thinking about models this way, we instead are pouring all of the data into some sort of Keras model, something with a deep neural network, where we lose the ability to deal with missing data and where we lose the interpretability. Well, we could also maybe make models this way. A lot of things can be solved with domain knowledge. So all of this is great, but you probably don't want to go to JavaScript and write all the code to do these sorts of models yourself. And also, we did all the math before manually. That's something also we probably don't want to do. And lately, there's more and more packages that will do this for you. And I just want to show a little bit of a glimpse of one of my favorite ones called Pomegranate. This is what a Python code for Pomegranate might look like for the disease example that I showed you before. The idea is you import the library. And the library has support for objects that represent a distribution. And in this case, the first thing I write down is the health. You either have the disease or you do not. This in total is a discrete distribution. And given this distribution, given your health, then I know the possibility of getting a positive or negative test result. Assuming all these things are known, you can just fill in these things and you have objects that represent distributions. So remember, we had 4 nodes in the graph. We had something in the center for the health and 3 edges for the tests. Those are represented here. And you can give these nodes names. These are just distributions though. If you want to turn it into a network, well, then you have to call Pomegranate, make it a Bayesian network. You say add these states. These are how the states are connected. And then you tell the network to go ahead and bake itself. Hopefully it's clear this isn't a whole lot of code. And the main work you have to do before you do any of this is you have to have values for these probability things here. But you can do that with something like pandas. Once you have something like this, you can tell the network, hey, I know that the first test result was positive. Give me all the probabilities left in the system. And it's smart enough to recognize that if you say that this test result is positive, that then this node, of course, doesn't have any uncertainty anymore, but the rest will just update. And you can do it for one thing that's known, but you can also do it for 2 things. And everything updates accordingly. You can even do it in a fun way, where one of the tests is positive and one of them is negative. This will be very confusing for your health outcome, which is also kind of what you would expect. I like this way of modeling, and I hope that I've made you at least curious to see what the Pomegranate has to offer. Right now, I've just looked at a discrete probability Bayesian probabilistic graph, but Pomegranate also has support for things like hidden Markov models and stuff like that. Seriously, besides scikit-learn, I think this is my favorite machine learning package out there. So now let's consider the riddle that I was talking about before. I hope the example I just showed you made you a little bit enthusiastic. But let's now consider another way of thinking from the Bayesian school. It's also a little bit mathy, but hopefully it will help you think about problems a little bit differently. So imagine that you're operating a customer service desk. And let's also imagine that you work for some horrible internet provider and that customer service only allows customers to speak to a disappointing serviceman after waiting for like 15 minutes. Maybe not the most realistic example, but it's a nice example, I hope. And that means that you will only measure the people who are willing to wait for 15 minutes. Everyone else you'll just not measure. And the question then is, given that we have this biased data set, we only see people that were waiting for 15 minutes, can we say anything about the waiting time of everyone? And the key thing here is that I find interesting about this riddle is we have very biased data, but we know how the data is biased. That means that if we want to learn something, we should be able to incorporate this fact. So let's maybe think of a model, something that helps here. Depending on where you went for college and depending how well you know probability theory, you may have seen this before. This is an exponential distribution, and you can use this to model the waiting time. Lambda is some sort of parameter, and if that parameter is high, then it's more likely that the waiting times will be larger. Here's a picture of an exponential distribution for different values. I think the blue line is for lambda is equal to 4, and the green line is for lambda is equal to 10. The way you should read this, let's zoom in on the blue line, is the likelihood of waiting for 2.5 minutes is this value, as opposed to waiting 1 minute would be this value. I really hope you guys can see the mouse, by the way, but I'm sure you can. But that's the idea. So this is nothing more than quantifying how likely it might be to wait this long versus that long. And that's dependent on some parameter. And in this case, I would like to know that one parameter given our biased data set. And this is where the tricky thing comes in, because usually if we just had a system like I just showed you before, we could usually do something like maximum likelihood. Or we could say something like, okay, let's suppose that we had one data point here, one data point there. Then we can compare lambda is equal to 4 to lambda is equal to 6, and maybe do some sort of grid search to figure out what lambda is the best. But I know that my data points will only be from this region, so I need to compensate for that somehow. Because let's say that I have a waiting wall for 15 minutes, then I know that I will only measure the points that are around here. And I need some way to make sure that my gradient search is still balanced. We haven't compensated yet for the people who wait for a very short time. And this is helpful, but we might still need to do something extra. And again, this is one of those tasks where you can't just chuck it into a linear model. You have to think about this from a very probabilistic point of view. So since we're playing with this probability distribution anyway, let's see if we can sort of add our own factor, something that makes it easy to work with for our data set. Because one thing that we can do is, because there's a probability distribution, you can say, well, how about I just integrate this probability distribution for the region that I am in? So let's say I know for sure that the waiting times that I'm going to measure are going to be larger than some value m. Well, what you could then do is you can say, well, take this probability distribution, leave the lambda in, but just integrate x such that we only take values larger than m. And then instead of optimizing for this function, you just compensate for the distribution that you're no longer interested in by dividing it. And this is a very simple trick because we're aware of the probability densities and all this. But just by applying this trick, we can suddenly work with very different distributions. In fact, here's a picture of it. Here you see, given a certain value for m, I think I picked it at 4 here. Here is the distribution for different values of lambda, where I cut away all the probability mass before, so all the mass I had here has been cut away and has been moved into the remainder here. Now, because this distribution is the thing that I'm actually measuring in, I can suddenly apply gradient descent in this space, and everything will actually go ahead and work. And the nice thing about these distributions is I can be very flexible. The value for m is not set. I can make such a distribution for when m is equal to 4, when it's equal to 6, or when it's equal to whatever. I can still model a distribution this way. So what we will then do, just as a mental thing, this is a situation that we have. Suppose that we know that m is equal to 4. What I can then do is I can say, okay, let's suppose that the one data point we saw is equal to 5, and another data point was equal to 10. I can then say, what's the likelihood for the green line? Well, you look at this value for the 5 in the green line, you look at the value for 10 in the green line, you do this for the orange one, you do this for the blue one, and then for every single value of lambda, you get a likelihood score. And what you can do is you can then make a plot of all the possible values for lambda and all the associated values for the likelihood. And that's what you see here. Here you see the distribution for lambda, supposing that we saw these points, supposing that this was the border. And the very nice and pretty thing is, I mean, this is on its own right, this is very interesting because we've quantified how uncertain we are. But another nice thing appears is that when suddenly this data set becomes 3 times as big, the distribution becomes a whole lot more pointy. This suggests that we have much more certainty in our estimation for lambda, which is kind of exactly what you want. You want this belief that you have to become more and more thin the more and more data you see. I realize that all of my examples are somewhat mathematically involved, but I hope at least I've touched upon some of your intuition to sort of look at these examples later on. At least personally, I found this example to be very revealing once I've implemented this in Python myself. Doing this really helps you appreciate distributions and sort of how belief update works. Now, I've kept the example somewhat abstract, but what I will do now is I'll try to give an example of something that you actually could have in real life. Some sort of a Bayesian system that actually could go to production if you think about it. And the slides I'm about to show you are from a presentation that me and a colleague did. And it's worth to note that I don't work for Blizzard. I also do not work for Nintendo. And I also do not work for Microsoft. What I'm about to show you is something that could go to production, but it is more of a hobby project. And I have to mention this because I'm using a patented algorithm. TrueScale apparently has a patent on it, and I'm not really sure I want to figure out what that exactly means. So let's talk a little bit about how machine learning usually works, and then let's talk about how a system needs to work for video games. Usually when you do machine learning in practice, what you do is you say, hey, there's a certain type of event. There's a certain type of function that I apply to that event, and then I have a prediction. So let's say in batch, I've trained this one function, and this is, let's say, for house prices. And every time I see a floor plan, I have to predict what the house price might be. This is something you very typically see. You have something in our studio, you train a nice little model, you push the model to production, and then every time a new event drops by, we have a prediction. The downside of this is this function doesn't update as we see new data. We probably have to run some sort of cron job or some sort of batch algorithm that takes in all the new data we saw earlier to update this one function. But in real life, we often have a slightly different scenario. In real life, we often see some sort of event, and then we want this machine learning algorithm to immediately update, to immediately become a new thing. And if at all possible, it would be nice if we had a system that could update instantaneously instead of having to wait. Because if you think about it, if you have a streaming algorithm anyway, then maybe you don't have to start doing batch at all. You can just feed it the first data point in the CSV file, go through all the data points in there, push it to production, and you never have to update the system. If you solve streaming, you might solve batch. But then we have to talk about how we maybe want to do machine learning in a streaming setting. So with that in mind, let's try to do something Bayesian, and let's try to do something streaming. And let's pretend that we're doing something for video games. So let's say this is our enterprise use case. There's a large queue of people that want to play video games, and we are this video game service. And these people that come in, they want to battle against people that have the same skill. So we have to figure out, just by looking at 2 people playing a video game and seeing who won, what the skill might be of every single player. So we need to estimate the player skill somehow, and we need to learn this from a stream of match outcomes. And preferably, because people play a lot of these small video games in succession, we don't want to wait for a batch algorithm of some sort. We just want to see a video game being played, and after that, update the entire system instantaneously. So the first part of the solution might be to realize we can resemble skill in different ways. One way to represent skill is to say, well, we have some sort of number between 0 and 1 being very good players and 0 being very bad players, and your skill is just a number along this axis. I mean, that's a representation for skill, but you lose a lot of information. Instead, if we focus in on a distribution of skill instead per player, then we actually know a whole lot more. For example, we can say something in the order of, well, for the blue player, I might have an estimation that the blue player is average because the blue player maybe didn't play a lot of video games. But even though the average is very similar to the green player actually did a whole lot more games, and therefore has a more spiky belief. We're more certain about our estimation for the green player than for the blue one. So when we're going to keep track of skill, I propose that we're going to keep track of a distribution instead of just a single skill point. What you can then do is you can say, well, I've got this player 1 and I've got this player 2. And let's pretend that these two players are going to battle it out against each other. This is the one-dimensional distribution of skill for player 1, and this is the one-dimensional distribution of skill for player 2. And I can combine these two to make a two-dimensional distribution for the skill of both players. In this case, what you can do is you can just say, let's pretend that player 1 and player 2, their skill is independent of each other, and just sort of multiply these probabilities out on a two-dimensional plane. And that way you've got a 2D distribution. Well, in hindsight, if that was the two-player distribution, what you could do is if player 1 has 1, then you can say, well, as an update rule, how about we remove probability mass from the area that's no longer likely? If player 1 has 1, then probably the skill of player 1 is larger than the skill of player 2. So you take the diagonal line, you take some sort of error margin, and you just cut away mass in the area where it doesn't belong. This seems like a pretty nice thing you could do for an update. And another thing to point out is if player 2 won, you just cut away mass from the other area. And if there's a draw, then basically you say, well, it's likely that these two players have the same skill, so we should cut away mass that's far away from the diagonal. We now have an updated belief for two players. And if we want to have this in a system, the only thing we have to do afterwards is we have to map it back to single players. And that is relatively easy if you just draw it out. What you can do is you can say, hey, map all of this mass back to player 1 and map all of that mass back to player 2. And automatically what you kind of get is that player 2 will have more mass in the area where it's bad because it's a losing player, and more mass will appear here in the area where player 1 has 1. And this is consistent if the other player has won or if the other player has lost. And if you want to try this out, you can write a very small Shiny app. In fact, if you click to this link, you'll find it. And you can actually simulate to show that this works. I've got two Pokemon pretend players that are battling it out against each other. And what I've just done is I've just generated a whole bunch of samples. I've removed samples from here, from this area, if Pokemon 1 has 1. And I just look at how this distribution updates. And you can see the moment this player won, there's more mass towards this edge and less mass towards here, and vice versa. There's a very beautiful thing that will happen though, because let's now look at a slightly different example. Suppose that we knew before that one player was probably average, but the other player was actually quite good. Then suddenly, if player 1 won, the player who was supposed to be pretty good, then these two probabilities don't really update much. And this makes sense. If a player that's very good is playing against a player that's very average and the good player won, then our beliefs of those players shouldn't be updated. However, if the player who was supposed to be average suddenly won from the player who is supposed to be very good, then suddenly the update is much more forceful. We have just learned a lot more information because an average player is not supposed to be beating a good player. The only way that can happen is that this average player is probably quite good. Notice that the update here is a lot bigger than the update we saw before. We get this benefit for free by thinking about distributions this way. So what you then do is you simulate this out properly. And instead of just 2 players battling it out against each other, you simulate this as if 100 players were battling it out against each other. And what you can do is you can sort of come up with a pretend data set where player 0 has skill level 0 and player 100 has skill level 100. And you can pretend they're just going to be battling it out against each other. And after a couple of hundred random matches and maybe some sort of probability rule that updates like this, you can look at all the different distributions you have for different players. And I believe when I was running this was for 100 players after they played a 100 game with this probability system trying to figure out their skill. And this was after, I think, 1,000 games. And the nice thing that you see from this system is that indeed it does seem to converge. It is able to sort all these players in the appropriate way. So just by doing this with simulation, we can confirm that this idea works, which is very nice and convenient. So when you have this in your head and you think the system really works, obviously the next thing that you will go ahead and do is you will download all the Pokemon. Why wouldn't you? And you're going to see if this actually works. The nice thing about Pokemon is there's these APIs that you can just use. There's this lovely little website called pokeapi.com. I think this service might be down. The guy that was running it said it was costing too much because people were calling the API too many times. So what you can also do instead is you can go onto Kaggle to find this data set. But the Poke API will give you all the Pokemon out there with all the health points and the attack points and defense points and what Pokemon is weak against other one. That information you can just download from the internet. What you can also do is you can go to fan websites, especially if you go to Reddit, you'll just find this formula. And you'll find people who have reverse engineered the Pokemon video game on the Nintendo. And what you can then do is you can calculate, given a certain Pokemon, given how many hit points it has and how much damage the Pokemon does, you can sort of calculate how many turns one Pokemon might outlast the other. For all intents and purposes, this formula isn't too terribly important. But one thing that is fun is that I have a way to simulate if 2 Pokemon will fight each other, which Pokemon might win. So I applied this system, the thing I just described to you, and I applied it to the Pokemon dataset just to figure out mathematically once and for all what is the best Pokemon. This is what the posterior distributions look like. And a comfortable thing was I figured out that Magikarp, according to my algorithm, is the worst Pokemon, and Mewtwo is one of the better ones. Now, obviously, there's probably more scientific ways to judge an algorithm, but I figured this is not bad as an initial trial. This was pretty cool. I really like this example to sort of explain how you can update things. Because there is a whole general mass to all of this. Because I hope it's very clear, we have a distribution of skill, and after we saw a game, we updated the skill, and we can do this in a very, very streaming fashion, which is cool, because that means we don't have to do batch algorithms, and we can just keep the system running. Designing the algorithm in this case became a whole lot easier when we admitted that we wanted to quantify the uncertainty, which means that we must work with distributions as our state, not just statistics. And this really, really, really fits in well with the Bayesian mindset. Before, we were trying to calculate the distribution for how many people were waiting. And in this case, let's just say that theta is the distribution for a skill of a certain player. And D is the data that we see. The way you can sort of look at it is you can say, well, the belief that I have of the skill of a player after having seen 3 games, well, it's the initial belief that I have in the beginning. Maybe in the beginning, I think all players are equal. And these probability functions that you see here, they're just update rules to this original probability that you see here. And you see, if I've seen 3 data points, the new belief that I have is just the probability distributions multiplied. And if you think about it, the belief that I have before seeing the second data point, we can call it the prior. This is the prior that I see before I saw the first data point. This is the prior that I see before I see the second data point. This is the prior that I see before I see the third data point. And lo and behold, there's a recursive relationship, which means that for a new data point to come in, this is the state that we need, which is just a distribution of skill. And we only need one simple update rule to then be ready for the next one. And this proves that any Bayesian algorithm that can be written down in this form can also run as a streaming algorithm. And this is a very powerful thing. a lot of systems benefit from being a streaming algorithm. And what we hopefully have pointed out that's very clear is we just saw a very nice example of exactly this. You can do it in batch, but if you can do it in streaming, that might be preferable. Now, I like this example a lot. So what I would like to do is I would like to make this example a little bit more complicated to show that you can actually build pretty decent architectures for streaming situations with this Bayesian mindset. So before we were just considering video games where one player is battling it out against another player. We can also consider a more difficult problem where teams of players are fighting against teams of players. And to make it even more difficult, if we pick Heroes of the Storm, then you also have a situation where different team members can have different roles. Because not only now are we sort of worried about different players being better at this game than other players, I also want to have a system that doesn't put 6 healers against 6 assassins. Like, obviously, the healers will lose. So this was our enterprise use case before, and now we've got an enterprise use case that's a bit more like this. Not only do we have a queue of players that we don't want to have them waiting for a very long time, not only do we want them to battle against players of equal skill, we also want to allow each player to say, I want to play as this character. And suddenly it's a whole lot more complicated, as you might be able to imagine. However, you can consider this sort of streaming system that is chopped up into small bits that's able to do something like this. You have a giant queue of people, and this giant queue of people are people who are waiting. We retrieve some sort of player state that we know. This is something we calculated before. Depending on your skill, we're going to map you to some sort of bucket. If you're in this bucket, you're not the best player. If you're on that one, you're a pretty good player. The size of this bucket and how we're binning this, that's something we can do in A/B testing. Next, what we can do is we can just wait until one of these buckets has 10 people in it. We can then assign those 10 people into 2 different teams. We can have them battle it out, and then we can just update all of these states again. What I hope is somewhat clear is that even when things get more complicated, we can just chop up the problem into separate bits. And as long as we're using distributions instead of just numbers, we can deal with uncertainty in a very elegant way. I'm keeping an eye on the time, so I don't want to talk about this example too much because you can find a video of me talking about this problem as well. But just to zoom in on one cool part, mapping a skill to a bucket is easy. But what you can also do, if you've got team A battling it out against team B, you can still apply these update rules. In this case, you see that there's a couple of players that had a certain skill, that's the blue dotted line. And you can still make an update rule where one team wins and then it goes from this dotted line to this yellow line and the other team loses. And you can sort of design the nudges in any way you want, but just having these distributions makes everything a whole lot easier. So I'll just skip on a lot of things here because I kind of want to talk about the last part, which is what I think the future might be. Because I hope at least I've inspired you to think more about distributions instead of just models. There's these moments when Bayesian thinking really shines, but the main problem that I think I see in a lot of systems is that lots of modeling these days consists of just pouring data into a modeled mold. I have a data set, I did a whole shit ton of feature engineering, let's just give it to a random forest and that'll be that. This may not be the best way to approach it, because instead what you might want to do is you might want to be very explicit about the model and just say, I think the world works this way, I'm going to model it as such, and then see how it works. And to give an example of this, there's a data set that comes with RStudio. It's called the chick weight data set. If you go to RStudio and just type in chick weight, this is the data set you're going to get. There's a weight column, there's a time column, there's a chick column, and there's a diet column. And the idea is that you can measure this chicken had this diet on that time, and this chicken at this diet at this time had this weight. And you can make a plot of it. It'll look something like this. The goal of the data set is to do some sort of A/B test to figure out which diet helps the chickens get as fat as possible. So knowing that the data set looks something like this, it's a little bit strange that a lot of people start modeling this by just chugging into a linear model. They do something like, hey, let's make a linear model. The weight is dependent on the time and the diet, And this is the model that comes out. And when you look at the summary in the model, oh, look, there's all stars and everything is super significant. So this model might be correct. What I hope is somewhat clear, though, is that if you just think about what the model actually is doing, the model is all wrong. If I look at this data set here, it's not that if you belong to a certain diet, that across the board, the value of your weight is higher with some sort of constant. In fact, I would argue that all the chickens, they are born equally. It's not that because you're in a certain diet that here you have a sort of constant that needs to be added. But if I look at the output of this model, that's exactly what it's doing. So something we're doing here is super wrong. And if you're into R, then you'll appreciate the trick that I'm about to show you, because you can make it a little bit better. I mean, what you can do is you can say, take the chick weight data set, group it by diet, then nest it. And then for every single diet, make a separate machine learning model. And this would already be a whole lot better, because now what we're changing is for every single diet, we now have an intercept and a weight. So that's a whole lot better. But then still, I don't like this model much, because here I'm having a different intercept for a linear model for every single diet. And if I look at this chart, obviously the intercept should be exactly the same for all of these chickens. And in machine learning, it really feels like we can pour data into a predefined model, but it doesn't feel like we can define the model much. We're usually constrained to perhaps feature engineering and hyperparameter tuning, which granted is good enough for most problems. But even for the simple data set, I mean, modeling this correctly by just pouring it into a model mold, it's kind of hard. And the problem kind of is that popular machine learning libraries don't really offer a proper DSL for models. And if I think about it, I can take a piece of paper and I can just write down what I want. I want to say, well, we're going to model this weight, and the intercept, this beta 0, that's the same for all the chickens, but I just want this thing to be different per diet. I really just want the computer to look at this piece of paper and to do the rest of the implementation. I just want to have some sort of a DSL where I can just declare this as a model, and that then the computer will do all the feature engineering to make it work, and that this model will run. And as a modeling purist, I can look at this sort of landscape and I can say, look, your dog is broken a little bit here. If it doesn't do exactly this, you're not really being the best machine learning library for me. And here comes something I think is rather pretty. There is a package in R called Rethinking that does exactly sort of this. It's kind of a DSL. R has these freaky non-standard evaluation features that allow you to sort of parse the tree in a different way. But what this will actually do, here I'm defining that there's this thing called a weight, which is normally distributed with some sort of mu and some sort of sigma. And I can say that the mu is, well, some sort of intercept and some sort of slope. And the slope, that's dependent on the diet. Now, this diet is something that occurs in the machine learning data frame that I'm passing in here, namely in the chick weight data set. But very quickly here, am I able to declare these? This is sort of how the probabilistic system works. And here's all the variables I want you to sort of infer. And lo and behold, if I just type this in, this is what's gonna come out. It's just gonna estimate all of these different features for me. I can go a step further, because even though I like the model that I had before, what I would like it even more to have is that this error term, that also has a distribution where the error term also increases over time dependent on the diet and also has some sort of constant. And the nice thing about this rethinking package is that here I'm also able to just declare that. I'm saying, well, that sigma now no longer is a separate constant, but it's also something that we need to estimate. It also has a dependency on the diet and the time. I declare this, then a whole bunch of magic happens and it will compile the stat and all that, and it will go ahead and train all of these things on my behalf. And this is, I think, maybe the future I want to live in. Of course, deep learning and random forests, they're pretty great and all, and they solve a whole lot of problems. But there's a couple of these problems where I really specifically want to work with probability distributions. And I would just want to explain to the computer, this is what I mean. Now, please go ahead and build it for me. I don't want to spend all of my time writing my own for loops and working with tensors. I think that the computer should be able to do this for us. And maybe if you then want to model a house price, let's say, I can come up with a model that says, hey, the house price just depends on the price per square meter, and there's a couple of square meters in the house, and the square meters depend on the longitude and latitude of the house and the house type, and maybe the price per square meter, well, that depends on time, and I can sort of make a model for this bit, I can make a model for that bit, and maybe we can have these nice hierarchical models that we can explain to sort of stakeholders as well. And for that, Bayesian modeling would help, but also having a DSL that works something like this might help, even though rethinking itself is not general enough, I think. Yeah, and then I've got a proposal of what that might look like, but this was the main point I wanted to end on. I really think that if you have fun Bayesian models, and you can just find a way for the computer to make it very easy for us to declare these things, that these things might become a whole lot more popular and useful than the standard random forest that a lot of people tend to use. Now, I've went over this relatively quickly, especially at the end, because I wanted to leave a little bit of time for questions. But I hope to the very least I've inspired you to give this Bayesian school a chance.
That was awesome. Thanks, Vincent. I'm gonna open it up for questions. So if you want to type it in chat or you just want to unmute yourself, feel free. I'm obviously, as a video game nerd, I really like the examples. And I think that Rainbow Six Siege and Overwatch could use some balancing help in competitive mode, but that's just me.
Okay, so there's one fun question about it. So me and a colleague were at this conference presenting this, and we presented this at the Flink Forward conference and a bunch of other places. And suddenly we did get approached by these people who work at EA, and they were sort of pummeling us like, are you sure that our competitors are using this system? Are you sure that, kind of fun to talk to these guys. So they might become a client, we'll see.
Awesome.
But they're all pretty secretive about how their systems actually work.
Yeah, well, I've had not the greatest team balancing experiences in some of these games. So any questions? Does anyone want to unmute or type in chat? Just feel free. In the meantime, I know some people had to hop off for probably boring work stuff, but I am recording, so I'm going to send this out to everyone in a newsletter, hopefully by next week. So yeah, I do have a question. Have you had a chance to implement a Bayesian system like this in production with any of your clients at Go Data Driven?
Yes.
You can talk about.
Yeah, so a little bit of an NDA here and there.
That's okay.
There's two things I will say though. Part of the financial world does really appreciate being able to quantify your uncertainty very, very well.
Mm-hmm.
And then a parameter of a model, if you can say, hey, we're unsure about this parameter, or we're really, really sure about this parameter. I guess people who, what's the word? When you have a government agency that checks on a bank, that is a toezichthouder? Toezichthouder in English.
Like not the FDA,
Well, the government watchdog.
Okay.
But yeah, the FDA could be that.
For health.
Like they really like it. So this is not so much a production thing, but this is something that they do like data scientists to sort of at least try out. And there was one system that kind of went into production where you have to imagine that there was a clerk that needed to make a decision, and the clerk only knew 4 out of 10 variables at any point in time. So we just had to make a model that was able to deal with having more unknown variables than known variables. And that actually went into production for a brief moment.
Cool. How come for a brief moment?
NDA. Let's say that, suppose that you run an airport and you make a model on how the logistics of the airport works. Suppose you do this, you could. And then suddenly someone decides, oh, let's completely redo the left and right wing of the airport. Then, of course, the trained model doesn't work anymore because the airport works differently.
Right. So you have a paradigm shift.
That was the reason I took it off.
Right. That makes sense. All right. Anyone else have any questions? We've got a few minutes left. We could probably give you a couple minutes back. If not, thank you guys for joining on your lunch break or your dinner or wherever you are. For Vincent, thanks for joining us after your work hours. Again, I was recording, so I'll be sending this out. I'll stop the recording now.